So thank you, Superbeam. So we are on the schedule. Now will be my mentor, Marc Naeije, was talking about the satellite altimetry. He the first one that introduced me to the satellite altimetry. Marc, please.
Thank you, Captain Sommart. Nice words. We go back quite a long time, I think. And we're not done yet, so we're still researching stuff. Yeah, so my task to talk a little bit about altimetry, the satellite altimetry, and tide gauges. So that's why we have this this title. I don't have an overview, so we can just skip that. But of course, altimetry and tide gauges, I will be talking about that. Very quickly, how the altimeter works, or how the altimeter with its radar pulse sees the sea surface. Or actually, yeah, it measures a few things about the sea surface. And it depends a little bit on whether you have a calm sea or a rough sea. And then we look at the incoming pulses at the satellite. So if you have a calm surface, you have a very steep gradient here. So basically, this waveform grows from no reflection yet till the full reflection. And when you follow this line, yeah, you can get a few of these geophysical parameters from it. With a rougher sea, it takes longer for the power of the echo to come back to the satellite, and that's why you have a less steep waveform. Basically, this looks, let's say, less, maybe less rough, but it's the opposite. So these are the things that you can actually deduce from the returned echo from the altimeter satellite. Sorry, that was the wrong button. Okay, so basically, of course, this is a simplified thing we measure. Basically, we measure these kinds of things quite well, with a high frequency, I would say. And you get this kind of shape if you take, let's say, thousands of these samples together. So one thing is, of course, what we look at is the half height point. So here, and you know when it was sent from the altimeter to the sea surface, and when you get your echo back, you just see what happened with the half time of this height point, and that gives you access to the actual distance, the distance from the satellite antenna to the sea surface. Basically, your timing, of course, when your signal arrives back, and then just thinking this is with the speed of light, you can, of course, deduce the distance from this timing. Okay, there are a couple of more things involved, of course, but okay. Yes, so the steepness of this line here, this is giving access to the significant wave height, and the total power gives some measure of the wind speed. Actually, the backscatter is called radar backscatter, but that gives you insight in the wave in the wind speed. And then we go to this graph where we have the satellite. And yes, so we send the pulse to the sea surface, it's reflected back, and it is it's received at the satellite. Now, how can we deduce? So basically, this is the distance from the satellite to the sea surface. But what we want to know is the height of the sea surface. So we have to know the very precise position of the satellite. So there are a few things in this graph. So yes, the range is the thing you measure. Then the r, the small r here, that is the location of the position of the satellite with respect to some reference, basically the center of gravity of the Earth, but we use a reference ellipsoid for this reference. So and then so we do the range minus the height. The height of the so the range is this is the height minus the range. There are a lot of corrections involved. So your pulse, your electromagnetic pulse is going through the atmosphere, so it's delayed. So it's not exactly the speed of light. You have the ionosphere, you have the troposphere. It's all delaying your pulse, and you have to correct for that. Also, some corrections at the sea surface itself, because your waves are skewed and not nicely sinusoidal. But okay, let's so there are some corrections here. This is the position of the satellite, what we measure, and basically, if you take this height, subtract what you measure, then you get the sea surface height with respect to the reference ellipsoid, and basically that is in this this equation here. Now in this sea height, there is geoid. Basically, that is the most important signal, or at least the biggest signal. And there is dynamic topography. And the dynamic topography is your sea level changing because of the currents. And that is what you measure. So that was in a nutshell. What can you do then with these measurements from your sea surface? Well, you can put them all together and take the average. And that might look something like this. Of course, if you don't see this, and you would be asked, what do you see here? Probably the first answer would be, I'm seeing the bottom topography actually of the sea. Well, it's basically the geoid. This N is the largest contributor. And this is the mean dynamic topography. And together they make the mean sea surface. So it's not the bottom topography you see, but it is the mean sea surface, which is related to mostly to the gravity. So you're seeing indeed mountains and ridges in your mean sea surface, because this is a geopotential surface. So how does that work? Let's say your local sea surface is actually responding, or actually putting these plumb lines to parts where there's the most attraction. For instance, if you have a dense mass thing under the crust of the bottom topography, you will see that in the mean sea surface. And also, if there's a ridge, so there's extra mass, extra gravity, all these arrows will point to this extra mass, and that shapes your sea surface. So that is indeed what we see. So it's not that the local gravity is pulling more to the sea surface. It's just because of these plumb lines. Okay, so one thing which you can do with the data, just average, and then you get your mean data. But okay, that is basically the static part, so you are more interested in what is changing over time. So if you do a standard deviation or variance of your data, then the outcome is totally different. Then you get an image like this. And basically this gives the locations where you have the largest variability in your sea surface. And then you start seeing currents, the strong changing currents, like the Kuroshio, the Gulf Stream, and the Agulhas. Okay, mean sea surface, standard deviation. Are there things changing over time? So the trend. Now here we follow a few of what we call the so-called reference altimeter satellites. So that started with Topex, Poseidon, and then Jason 1, 2, 3, and now we have Sentinel 6. If you do a global average, it will look it will look like this. And of course, you still see it's not just it is a straight line. Yeah, okay, that's the regression, but there's more things happening. You can have strong El Niños that will change a little bit the signal. And basically what you also can see, if you take the regression to half of this time span, then yeah, when we started with mean sea level change, we came around 3 millimeters per year. But if you look at the end, then basically the line will be a little bit steeper. And if you take the last part, you will get to something like 4 millimeters per year. So, and if you combine the whole time span, you get something in between. So basically, this also indicates that there is a kind of an acceleration going on. Here we compare the time span with the time span we have with tide gauges, and yeah, this is just a small part of this. Here we go back to let's say 1900 up to now, and we with our satellites, yeah, we only fly like 30 years now, something like that. We recently had the 30-year symposium on altimetry. Okay, so that was a little bit about altimetry. Of course, it's more interesting for you if you see some results. From tide gauges, well, okay, there we have had a few returning pictures of this. So tide gauges measure sea level with respect to a geodetic benchmark, and yeah, they normally operate as a float in a pipe or a stilling well, and nowadays you will have acoustic or microwave radar for the tide gauge. But of course, the most important message with the tide gauge, if you which measures sea level, and I also said altimetry measures sea level, they're not measuring exactly the same thing. As we saw with the altimetry, it is sea level, but with respect to the reference ellipsoid. So we call that an absolute sea level measurement. And the tide gauge is connected to the land. So basically it's measuring both land motion, vertical land motion, and sea. So it's the sea changing with respect to the land. So that is what a tide gauge is seeing. And that is a bit more explained in this on this slide about the vertical datum transformation. Basically, this is meant to connect all the information we have, information on the ocean floor, information on what is measured from land, measured from satellites, and actually they all measure something else. Well, not entirely true, they measure the same thing, but with respect to some reference, and all these references are not, they don't coincide, so we have to make these connections as we see it here. Okay, some quick commercial for our database. If you are interested in using altimetry, of course you can go to all the agencies, the space agencies that provide the altimetry. But we have TU Delft together with NOAA and EUMETSAT, we have basically built our own system, and we combine all altimetry, make them aligned, some consistency over time, and you can apply the same corrections. So, of course, in the end, you want to actually combine everything, and then I would recommend RATS. Okay. And now we come to some results I have been trying to get for our Gulf of Thailand area. It's actually based on some other work I did for ESA. We do a CalVal for Cryoset. And basically what came out of this study, there's also a paper published, is that it's a very stable system, stable platform. We have compared it with the reference satellites, with JSON-1, JSON-2, JSON-3, and Sentinel-6. And what we see is some deviation of a few 0.0 something millimeters per year if you compare the reference satellites with geosets. And Cryoset. And the most important advantage of using Cryoset is that we have a very long time of measurements. It started in 2010 and it's still working. If you talk about the reference satellites, you have to combine. If you want to have the whole thing back to the early start of Topex Poseidon, 1992, you have to combine all these missions, and that's not always easy. So if you have one platform which is guaranteed stable, and you take that time period, then I actually personally would favor that a little bit more. So that's why I'm introducing this. And the only thing I want to point out in this graph, because this is about some results from that study, is that we have here the comparison. So this is what we see here. So so we have a difference of 0.07 millimeters per year with the reference satellites. So from now on, I will be using Cryoset, and I'll show you some results for that. So for this period, and it's important that you indicate the period, because if you take different time periods, you just get another answer for your mean sea level. Basically indicating, so there are two things about mean sea level. You already see it here. So mean sea level trend. So the tilt in the mean sea level, it's not a uniform thing. So it's not just one color here. So it's also a very local thing. Some places you have more of this sea level change, sea level rise, than in other places. And there are also places you can see some sea level fall. So one thing is it's not uniform, and also over the different time periods where you would look at it, you get some different answers. You can see that this is also something changing. So you can say it's like blah blah blah, plus or minus millimeters per year. But taking another period, well, it's nice to take a different period, so you can also see that there is acceleration in this sea level rise. Now, okay, so up to 2024, this is the whole period where Cryoset exists, and we took all the reference satellites, so that's the result on the left, and for Cryoset it's the result on the right. And basically there is not much of a difference. You can also see it in the mean sea level trend value. So for Cryoset we have 3.8 millimeters per year, and why there is a preference then to use Cryoset? That's also because Cryoset has a somewhat denser sampling of the sea surface, so you get a little bit more detail. With the reference satellites, you would have like 2 passes, let's say spatially going through the Gulf of Thailand, where it's 3 or 4 times as large with the Cryoset. Okay, so so we take the Cryoset, so we see a mean sea level change of 3.8. So what can you do more with the data? I already showed that, but now this is from the actual Cryoset data over this period. On the left, we have we call it this mean SLA. So SLA stands for sea level anomaly. So this is the anomaly with respect to a mean sea surface model. So there's still something, let's say, in the mean SLA. So the mean Caesar model is not, let's say, perfect or not exact. So it's still different. Would you be adding something like the mean dynamic topography? You get the actual ocean dynamic topography. Yeah, mean ocean dynamic topography. Taking the standard deviation, or also referred to as variability, you get the plot on the right. Again, still cryosat data. Now we have the nice currents here, the Crucio, Agulhas. Sorry, this is Agulhas, of course. This is the Gulf Stream, and this is the Crucio. Also the Brazil Malvinas. But you can also see if you go to Thailand, so that there is enhanced variability in the Gulf of Thailand. And that is a real signal. There's actually quite a large annual signal in the Gulf of Thailand. So here we see some seasonal average mean SLA. Basically put together 3 months for the seasons. And this is for the whole period. We just averaged the Januaries, we average everything in the February, etc., etc. So for every month we have an average. And here we just put it together for the whole season. So basically our seasonal climate average change. As I said, we can basically add back to our sea level anomaly the mean dynamic topography. Now the mean dynamic topography is a model, and that model consists of the mean sea surface and the geoid. But if you take those together, you can almost not see it in this on this picture. But these are, you get all these sort of round features in it. So you cannot just subtract it. So we have to filter it. So, but if you then put this together with the SLA, you have the actual ocean dynamic topography. So you will see how the currents flow. So time to zoom in on the Gulf of Thailand. So we start on the left with the tilt, or the trend in the sea level, and this is the wrong button. Yes, okay. Sorry for that. Okay, so we have the trend in the mean sea level in the Gulf of Thailand. So we have here 2.26. Okay, so the mean of our SLA, and here we have the standard deviation. So basically the blue one you saw before, but now zoomed in on the Gulf of Thailand. So you can see indeed that there is a variability in this area. Okay, here we also have this taken together our climate. So we averaged. We took the average January, February, etc., etc. So we get a kind of a climate. We can also call it the annual signal of what we have in Thailand. And you can see that it is a very strong annual signal. So highs also in the inner Gulf during the winter and in the fall, and in the spring and summer we have lows. And then I added back the mean dynamic topography. So now we get ocean dynamic topography, seasonal. I'll call it the climate model for our seasonal ocean dynamic topography. Nice. Now you could actually deduce currents from this. Basically, if you know a little bit about geostrophy, we go from highs to lows. We are on the northern hemisphere, so these are circulations that go like this. Of course, it is. Yeah. Okay. So the altimetry or cryosat is not filling the whole Gulf of Thailand with a high dense information. Otherwise, we would have seen a bit more detail, of course. But this is the main gyre in the Gulf of Thailand. Okay, we already saw in the presentation of Wim talking about vertical land motion and how you can also deduce that from, well, on one hand, of course, the GNSS, but on the other hand, combining the altimeter, or let's say the SLA, with the tide gauge. And you can make all these kinds of combinations. So indeed, vertical land motion from altimetry minus tide gauge, or let's say an estimate of a tide gauge or simulation of a tide gauge by combining the altimetry with the GNSS, VLM, etc., etc. But why can we do that? Why is this kind of allowed to do that? Well, basically we can set up this RSL, so we call that regional sea level from the tide gauge, and there are a lot of components here. One is the mass redistribution. We have some steric component. Then there's GIA, and you have a GIA, which is a combination of a global sea level GIA and a vertical land motion GIA. And then then of course we have some residue or something that we maybe not understand or don't know about what processes are going on this location are. And so if we're going to make the combination, for instance, if you want to have this salt minus TG is VLM, there are a few things that actually fall out. So because they are the same for both measurements or both systems. So of course these fall out. Then this is a bit debatable whether the rest falls out, because that might be different, because this is something we don't know. But okay, for now we just take it as the same. And then we have of course the combined definition for the GIA, and basically that also falls out. So then, indeed, we can have this salt minus TG is VLM, and we don't have to apply any GIA, because that also falls out. Now, well, I'm not sure. Okay, I'm already over time, I see. But this is a plot you saw from Wim's presentation, so I will very quickly go through this. But this is what we noticed at Phuket, that where we tried this thing as altimetry minus TG is VLM, and basically we came to the conclusion that is really fitting. Basically, very good actually. I think the most important thing is that we know that the tide gauge is connected to the bedrock and the GNSS as well. So that's why this is really working. With sediment, that is a bit of a different story, I guess. Okay, so we have some simple models. We fitted these signals, and so the conclusion was that there's a pretty good match between all those different measurement systems. Okay. Going back to, well, this is not the Gulf of Thailand, of course. This is the Andaman Sea. Basically, if you take this area and we call it the Andaman Sea, then we are at 1.82 millimeter per year as a tilt. And here we directly compare the altimeter with the tide gauge over the same period. If you look at this annual signal, this is not. It looks like the same model, but of course this is based on the information that is in this graph, and here it is based on the information on the tide gauge, and it is, well, it's actually spot on. So it's really the same. So what is going on here? So if we wanted to have the salt or the SLA minus the TJ, so we have 1 minus 3. So we have -2 for the VLM, so that would be a subsidence of 2 millimeter per year over this period, so under 2010-2024. But I think this is quite okay. This is what we have found before. Okay, I know we have more information, more tide gauge information. I did not have the time yet to look at that, but of course that will be the next step to look at that. I just, for this exercise, I just took the data as it was available through the PSMSL, so that is the general database for tide gauges from NOC. This looks like a kind of a strange result, perhaps because if you here do the salt minus TG, basically you end up with some uplift. But okay, that's yeah. The question is, do you trust? Well, I trust the altimetry. Do you trust the do you trust the tide gauge? But okay. But I also here this annual cycle is more or less or almost the same. So this looks good. So we had in the Gulf found 2 other tide gauge systems. One is at Colac. Here we have it's again of the altimetry top plot and the tide gauge bottom plot. So here it would be something like -3 millimeter per year. So this is a clear subsidence. And a little bit more to the south, Komatapon. Also some subsidence here, like 1 millimeter per year. Okay, then the conclusions. Sorry that I took a little bit longer than anticipated or given. Okay, altimetry shows absolute sea levels in Southeast Asia, well, rising due to climate change. What we see for Thailand in the Gulf, it's on average 2.3 millimeters per year. We have 1.8 in the Andaman Sea. And it is interesting to see or to conclude that it is lower than the global average of 3.8 millimeters per year. And I recall from our earlier study, well, that's 10 years ago, that it was the other way around, that you had the average was around 3 millimeters per year, and in the Gulf it would be something like 4 or 5 millimeters per year. So basically this is good. This is the good news. So, but then still the question is this threat? Is this a threat to Bangkok? Of course, not now. We have a somewhat smaller absolute sea level rise, but we are also depending on our land motion. Most of Thailand, what we see is experiences land subsidence. One is are close by megathrust earthquakes and also the groundwater extraction, and that increases, of course, the RSL. Well, this is a bit of advertising all our techniques and how we can intercalibrate them. So I will not read that out loud. So yeah, that is basically it for now. So a bit of, well, okay, so I would not say it's good news because sea level is still rising. But globally, we see an acceleration somewhere in the 2017, 2018 for the global sea level, but not in the Gulf of Thailand. So it's basically smaller there at the moment. Yeah, okay. I will leave it to this. Thank you. Sorry. Yeah, questions. Is there time for? Is there a burning question? Yeah, yeah, okay. So that's fine. That's fine. And I will not be gone after this talk, so I will be here. So if you want to ask something, please do. Thank you for your attention.
Thank you, Mark, so much. My one of my mentor. So next will be have a break. But before break, I would like to tell you that Mark said it's good news that the civil rights in Thailand, in Gulf of Thailand, is not that much to something compared to the global average. That's good news. But for the case of Bangkok, civil rights is not the main payer. The land subsidence from INSA, from Dr. Rupao is the main payer. So after we have a break, so we learn about something about INSA result. Dr. Rupao will talk, and Kun Anirudh from the Department of Groundwater Resources will be have some result of the study. So yeah, we can have a break now for 15 minutes. Thank you.